Hi, everybody. It's Professor Mitchell continuing with Chapter 6. In this video, we'll look at Section 6.5 on tree diagrams. In this section, we'll look at the tree diagram, a medical example, and then a quality control example. A tree diagram helps us represent the various events and their associated probabilities. The various outcomes of each experiment are represented as branches emanating from a point. Each branch is labeled with the probability of the associated outcome. For example, here's a very simple tree diagram. We represent experiments performed one after another by stringing together diagrams of the sort given in the previous slide. The probabilities for the second set of branches are conditional probabilities given the outcome from which the branches are emanating. And like with a lot of other things, this will make a lot more sense when we do an example. All right, so here's an example. Experiment consists of two selections. First, you make a selection at point A, which results in one of three different outcomes. And then depending on which outcome occurred at step A, you can get any one of these outcomes. Notice that the probabilities may be different, and that is supposed to be a 0.3, I believe, kind of a low resolution diagram. All right, so here's an example where we will actually build the tree diagram. This example has kind of a surprising answer, I think. The reliability of a skin test for active pulmonary tuberculosis, or TB, is as follows. Of people with TB, 98% have a positive reaction and 2% have a negative reaction. In other words, 98% test positive, 2% test negative. Of people free of TB, 99% test negative and 1% test positive. From a large population in which 2 people per 10,000 have TB, a person is selected at random and given a skin test, which turns out positive. What is the probability that the person has TB? All right, so we're going to make a tree diagram using these probabilities. The probability that the randomly chosen person has TB is 2 out of 10,000, or 0.0002, which means the probability the person does not have TB is 1 minus 0.0002, or 0.9998. The probability the person tests positive, given that they have TB, is 0.98. The probability they test negative, given that they have TB, is 0.02. The probability they test negative, given that they don't have TB, is 0.99. And finally, the probability that they test positive, given that they don't have TB, is 0.01. So now I am going to switch over to the tablet where we will make this tree diagram. All right, so here are all those probabilities we just went over. So now I'm going to go to a blank screen. So we're going to pick our person from the population. That person either has TB or they don't. The probability they have TB is 0.0002. The probability that they don't is 0.9998. All right. Now, suppose the person has TB. In that case, the probability that they test positive, let me just double check here, is 0.98. The probability they test negative is 0.02. And if we take a person who does not have TB, the probability they test positive is 0.01. The probability they test negative is 0.99. All right. So now we can think of there being 4 different outcomes. Number 1, the person has TB and they test positive. Number 2, the person has TB and they test negative. Actually, let me use better notation there. I'm saying and, so why don't I just use the intersection symbol? All right, number 3, the person does not have TB and they test positive. Number 4, the person does not have TB and they test negative. All right. So by the product rule, I believe we called it the product rule from the last section. For example, that said that the probability the person has TB and tests positive is equal to the probability that they have TB times the probability that they test positive given that they have TB. Okay. So in other words, to get the probabilities of these 4 outcomes, we just multiply across the branches. So let me get my calculator ready here. So first thing we're going to do is for the probability that they have TB and test positive, that's going to be 0.0002 times 0.98, which is 0.000196. Okay, the probability that they have TB and test negative, that would be 0.0002 times 0.02, which comes out to 0.00004. The probability that they don't have TB and they test positive is 0.9998 times 0.01, which is 0.009998. And finally, the probability that they don't have TB and they test negative is 0.9998 times 0.99, which is 0.989802. Okay, so now we have all the information we need to answer the question. The question was, a person is selected randomly from this population and given a TB test and they test positive. What is the probability that they have TB? In other words, what's the probability they have TB given that they test positive? All right, well, using the conditional probability formula, that would be the probability that they have TB and test positive divided by the probability that they test positive. Okay, so that probability in the numerator corresponds with one of these outcomes, the first one. This one here, right? So this is going to be 0.000196. Now the bottom probability consists of 2 different outcomes. Testing positive means one of 2 things. They tested positive and they have TB, but it's also possible they tested positive and they don't have TB. So we need to add those 2 probabilities together in the denominator. All right. So now we'll crunch those numbers. Let's see. 196 divided by. Okay, and that probability comes out to about 0.019. Now let's think about that for a minute. You pick a random person out of this population, give them a TB test, and they test positive. The probability that they actually have TB is not even 2%. It's kind of surprising, right? And I believe the moral of the story is for a condition this rare, you need a test that's a lot more reliable than the one they have here. Either that or take the test twice. That would help a lot. Okay. All right. Next example, a box contains 5 good light bulbs and 2 defective ones. Bulbs are selected one at a time without replacement until a good bulb is found. Find the probability that the number of bulbs selected is 1, and then 2, and then 3. So once again, I'm going to go over to the tablet. All right. So we have 5 good bulbs and 2 defective ones. So I'm going to pick my first bulb, which is either good or defective. It's good with probability 5/7. It's defective with probability 2/7. Now, if the first bulb selected is good, then we stop, because remember the object of the game is to keep picking until you get a good bulb. If it's defective, we keep going. Now at this point, we've taken out a defective bulb and we're not going to put it back. So now we have 5 good bulbs and 1 defective bulb. So the probability of picking a good bulb would be 5/6. Probability of selecting a defective bulb would be 1/6. Again, as soon as you pick a good bulb, experiment stops. Now, suppose that you pick a defective bulb and then pick a defective bulb again. At that point, all you have left are 5 good bulbs. So really, there's only one thing that can happen with probability 1. You're going to select a good bulb. Okay. So now we can find the probabilities of selecting 1 or 2 or 3 bulbs. The probability of selecting 1 bulb is equal to the probability of selecting a good bulb on the first try. That probability is 5/7. The probability of selecting 2 bulbs means first you picked a defective bulb and then you picked a good bulb. So from the tree diagram, that probability is 2/7 times 5/6. Which is 5/21. And finally, the probability of picking 3 bulbs, that means first one was defective, second one was defective, third one was good. And that probability is 2/7 times 1/6. And you can throw in that 1 or leave it out, it doesn't matter. So 2/7 times 1/6, which is 1/21. So there are our 3 answers. The probability of picking 1 bulb is 5/7. Probability of picking 2 bulbs is 5/21. The probability of picking 3 bulbs is 1/21. All right. And that's going to do it for section 6.5. Tree diagrams provide a useful device for determining probabilities of combined outcomes in a sequence of experiments. And that'll do it for this section. We'll see you next time.